Electromagnetics, Poisson's equation. Actually, this video is I'm redoing because previously made videos has a lot of multiple errors in the document prepared for these videos. Part of the confusion came from the difference between Gaussian notations and the international standard right now. Originally, Maxwell's equations and the Gauss theory were developed using Gaussian notations, and dielectric constant and magnetic constant are all different. Sometimes you get the 4 pi where you don't see it in the international standard. So that's the old folks learned that Gaussian notations, but now it's a standard international standard metric system. So I think we needed to correct the document multiple places. So this run is redo for the previous version. Previous version was off the series already, and this should be the one used right now as an international standard. Okay, so using the international standard, the Poisson's equation is this way, and this can be epsilon or mu, depend on dielectric constant and magnetic constant. And this triangle is same as inverted triangle square. So this is the double derivative. Where this triangle come from? It's a gradient and divergent. So divergence E is rho over epsilon, and electric field is defined by the negative gradient of the potential phi. Okay, so what does this mean? Okay, this means the potential and the density of charge are related. And if you have a potential function, you take a derivative twice, you can find out the distribution of charge. The other way, if you have a distribution of charge given, you take an integral, then you can find a potential. Once you find a potential, you can get electric field. So depend on how the charge is distributed. For example, say you have conductor and charge is distributed here on the surface. So that's the one-dimensional rho x. So what happens is potential is going to be something like this. Okay, so this is going to be the phi x, this is going to be rho x. So they are related. Okay, and we have to know, once we know the charge density, we find out potential and ultimately electric field. Once we know electric field or potential, then we should know the charge distribution in the space. That's what Poisson's equation is about. And what is this? Is electromagnetics all about Maxwell's equation? Well, you remember the Maxwell equation, the first two is divergent D equals rho and divergent V equals 0. So these are static electromagnetic field. See, it doesn't have a t time in the equation. So in the static world, this two equations useful, and these two equations, if you wanna solve the system, come down to the Poisson's equation. Once t comes in, then Maxwell's other equation kick in, like b over t. So the first half of electromagnetics you learn is a static system, which is Poisson's equation. Basically, the first two equation of the Maxwell's equation. You take it that way. I think that's a correct way to understand. So Poisson's equation is the differential equation. You have to solve the differential equation. So potential is given, that's easy, take the derivatives. But the charge distribution is given first. Then how do we get the electric field? Well, we have to solve this potential, then figure out electric field. Okay, so that's how this whole theory is organized, and that's the first part of the electromagnetics, static part of the electromagnetics theory. First two equation of the Maxwell's equation. Okay, now pretty much everything comes from this. Using this Poisson equation, you can even claim that F equals QE, and this is basically Coulomb's equation. Okay, once you know the electric field, you have a charge, then you know the force. Okay, so it's pretty much cover everything. That's what you have to learn here. Okay, now in order to solve this differential equation, we will get the integral format of Poisson's equation. Okay, integral format of Poisson's equation. So this one, okay, this derivative using polar coordinate, we change polar coordinate, then we will get this portion. Okay, and this one for large R, if you integrate for the large surface, it's going to go 0. So only remaining is this. So what happened is we can get potential by integrating potential's second derivative, which is related to charge density distribution. So this is basically integral format of Poisson's equation and integral. Okay, so basically this is it. Now complication come from this dielectric constant. This dielectric constant is actually, if in the vacuum, this dielectric constant is epsilon 0, but in dielectric material, as you know, epsilon equals epsilon 0, epsilon s. This is a relative permittivity, this is vacuum permittivity, and this is the dielectric permittivity. Okay, that's the official name. Now since E equal E plus is D, there are two contributors to the charge. Okay, and the contribution from the dipoles is going to be surface charge of dielectric material is going to produce the potential. Now we get into this deeper. Okay, what does it mean? Well, there is the dielectric material, and when under the electric field, it's going to accumulate surface charge, and these are charge, so it's going to contribute to the phi. And you have a Q here, of course it's contribute to the phi, but this surface charge also contribute to phi. Okay, so this is the basic equation, and you break down into this. So this is the relative permittivity, and this is correct format for international standard. Okay, the Gaussian notation is different looking, and that's where the confusion come from. So when you look at the internet, you have to know some use the Gaussian notation. It's getting less and less, but the international standard is this way. Okay, now what does it mean? The electric field is going to affect atom or molecule and pull negative charge this way, and positive charge stay there, or some molecule positive charge moved. Okay, so what happened is there is this act like dipole, the dipole vector P. Okay, so what happened is in electric material there's a dipole vectors running, and this is going to produce d flux going back. Amount of d flux and dipole vectors are same, exactly same. Okay, that's why they are not true charge. The true charge also generate the d flux. Okay, so we have two sources of d flux. The d flux, the one source is from surface charge in dielectric material, and this is sigma plus, this is sigma negative. And true charge, it's a monopole. And magnetic material, this doesn't exist. So it's all come from the magnetic material's surface charge. Okay, and that's why divergent B is 0. And I tell you why this here. Okay, now what does this mean? This means the flux come from the true charge, and negative sigma is going to absorb some of them, and less flux going inside dielectric material. But you have additional charge on this side, so this generate flux. So the overall, the picture is going to be D equals epsilon 0 E plus P, and D minus P equals epsilon E, and that's going to contribute to phi, because the electric field is gradient phi, means it's depends on the distance only, this distance only. If you give the voltage V, then divide by distance is going to determine E, and doesn't matter what's going on inside. Okay, so okay, we go back and take a look at again this divergent D equals law. What does this mean? This is only true charge. Why is that? Okay, so we have a P, but we have a flux generated by surface charge, and as you see, this is looping. Okay, so divergent for this portion will be 0. Okay, just like magnetic field, you take any surface, in and out will be zero when it's looping. Okay, so this part divergence is zero. Okay, so what we do is to show why only this is true charge. This is the equation to manipulate. See, d flux from the surface charge is negative p. This is the opposite direction. Okay, so we divide this into two parts and move this to this side, and since negative d sigma is plus p, so this way. So what happens is divergent d is divergent epsilon e, right? And within epsilon e, this the flux and p is going to be circling around the same quantity. It's going to disappear. Okay, so divergent E. So that's why divergent E is going to be true charge over sigma. Okay, so that's the reason why the sigma is a true charge. And for magnetic field, divergent B is zero because there's no true charge. And doesn't mean it doesn't generate any magnetic field. That zero means there's no true magnetic charge. Okay, only surface charge. Okay, so we see the effect of surface charge in this example. Suppose you have a dielectric stick within E, and it's create a dipole, and dipole is uniform. This assumption within the dielectric stick. Okay, so using Poisson's equation, we try to get this phi within the stick. Okay, the carefree use this and integrate. This r is the radius here, and we use this 2 pi r dr method for integrating. Then we get this equation. Now we take E is negative grad phi. We get E caused by dipoling. Okay, we get this one. So actual E is going to be external E, and this opposite direction E, this is sigma plus and sigma minus. Within EP is this way. So at the Z is 0, Z is this distance, we get this equation. Okay, now the same method apply this, and divergent magnetic material, divergent B is 0. The reason is there's no monopole magnetic charge. So everything you see here is the from the magnetic dipole charge. This is surface, and exactly same argument apply here. Is going through the same equation. Then H become this. Now magnetic case, there is a permanent magnet which is has a dipole M without this. So what's happened is within the permanent magnet, the H running this way here, and this is sigma m plus, sigma m negative. Okay, so the magnetization is this way, H is go this way. That means demagnetizing itself all the time. Okay, but this flux run from here, from negative side to the positive side. So it's looping, just like dielectric material. But H, as far as H goes, it's go against magnetization, and that's why the permanent magnet is going to be demagnetized over the time. Okay, so in order to avoid that, we put the metal and bypass all the magnetic field within the metal, and the metal get magnetized. But if you use a soft magnetization material, when it's removed, it's not magnetized, and that's a way we can preserve the magnetic stick magnetized for a long time. Okay, so you see this dipole effect. It's generate charge, and the charge generate a potential, and it generate its own electric field or magnetic field. Okay, so the divergent B is 0 doesn't mean there's no magnetic field or anything. It just means there's no effect from the true magnetic charge, but there are plenty of magnetic charge here, and that's why this causes the magnetic field, and that's called force. The force is the same way, magnetic charge times magnetic field. Okay, just like a Coulomb's law. So the magnetic material and dielectric materials are totally symmetric, except you see in magnetic world, you see hard magnetic material, which is even after you remove magnetic field, is still dipole. This dipolar characteristic is different between magnetic and electric world. Okay, mostly electric world, most of them is a soft dipolar. Magnetic world, a lot of metals are the hard dipolar, and some of them is anti-dipolar. That means it's generate dipole, the opposite to magnetic field, so it's repel. So once it's placed in magnet, it's repel from the magnet. Okay, instead of attracted. So there are some material difference. That's the only difference. But as far as electromagnetic field theory is concerned, they are all same. It's come from Poisson's equation that dictate potential and charge. Okay, I hope you enjoyed this video, and please check out the videos, and if you like, subscribe.